So back in 2017, researchers at Google basically realized that everything AI knew about reading a sentence was just fundamentally backward. Like they threw out the whole idea of reading left to right entirely, decided to process every single word simultaneously, and, accidentally paved the way for the large language models that are dominating the world right now.
Yeah, it was a massive accident of innovation, honestly. And if you're prepping for your natural language processing final exam right now, that 2017 paradigm shift, well, it's the climax of your syllabus, basically.
Sure.
But to understand why it happened, you have to understand the specific failures that led up to it.
Right, which is exactly our mission for this deep dive today. We're taking your course modules, so modules 5 through 9, and really extracting that core narrative because you've already covered the foundational layer, right? The text has been tokenized, it's cleaned, and you've mapped those discrete words into dense mathematical vectors.
Exactly, the word embeddings. But a dictionary of embeddings doesn't give you syntax. I mean, it doesn't give you context. The field desperately needed architectures that could actually model the underlying structure of language. The evolution of modern NLP is really just um, a chain reaction of architectural bottlenecks.
Yeah, and we're tracking that exact lineage today, like how the field moved from basic local pattern recognition to systems that can translate entire novels, and, the specific mathematical trade-offs engineers had to make at every single step.
Right, and it's funny because the earliest neural attempts at this didn't even originate in NLP. The field actually looked at computer vision and just borrowed the convolutional neural network, the CNN.
Which seems wild for text, right? Because in computer vision, a CNN filter is this 2D square sliding over pixels to find an edge. But text is a 1D sequence.
It is, but it makes sense when you think about basic text classification tasks. Things like spam detection or sentiment analysis. The signals there are often highly localized, like a spam indicator such as click here to win is really just an enneagram feature.
Oh, right. So it doesn't matter if that phrase is in the very first sentence of an email or the very last paragraph. Its predictive power is exactly the same.
Exactly. So for NLP, that 2D filter becomes a rectangle. It spans the entire embedding dimension of a word, let's say 300 dimensions, and just slides down the sequence, reading 2, 3, or 4 words at a time. It's scanning for local n-gram patterns.
Okay, so you run multiple filter widths in parallel, right? Like a size 2 filter hunts for big gram features, a size 3 looks for trigrams.
Right, and as they slide over the embeddings, they generate these feature maps that basically spike whenever they hit a target pattern.
Mhm.
But the really crucial operation for classification happens right after that, max over time pooling.
Okay, let's unpack this. Because the feature map shows every instance a filter found a match, and max pooling it extracts the absolute highest scalar value from that entire map, right?
That's right. It just grabs the strongest signal.
So is a CNN filter basically like a metal detector on a beach? Like the algorithm just scans the sand, and when it hits a specific sequence of embeddings that signals spam, the filter output spikes, and the max pooling is just the system saying, yep, we found gold, completely ignoring exactly where on the beach it was.
That is a perfect analogy, actually. Yes, it throws away the GPS coordinates. It reduces the dimensionality down to a single number representing the strongest evidence that a feature occurred literally anywhere in the document.
Wow, okay.
And this positional invariance is incredibly computationally efficient. You can even push it further by using character-level CNNs, which bypass word tokenization entirely to slide filters over raw characters. That lets the model learn morphological patterns and handle out-of-vocabulary misspellings naturally.
Because it's just looking at the letters themselves.
Right, but discarding the location data introduces a massive semantic blind spot.
Because throwing away word order is disastrous for actually understanding language. Like the dog bit the man and the man bit the dog have the exact same vocabulary.
And the exact same enneagram features if you just look at them as an unordered bag, yeah.
Right. The CNN pools over time, so it just loses the sequence entirely. So to move beyond basic document classification into real deep language understanding, we basically needed to inject the dimension of time back into the math.
Which is exactly what forced the shift to recurrent neural networks, or RNNs. Unlike the feed-forward sliding window of a CNN, an RNN processes a sequence one token at a time, sequentially, left to right.
So it's actually reading the way we read.
Basically, yeah.
Hmm.
At every time step, it takes the current word embedding and combines it with a hidden state that was carried over from the previous step.
And that hidden state is essentially the model's running memory, right? The math is just taking the previous hidden state vector, concatenating it with the current input vector, multiplying them by a weight matrix, and then pushing it through a tan activation function.
Exactly. So the state at step 5 theoretically contains the compressed semantic traces of steps 1 through 4.
Yeah.
You can even run bidirectional RNNs, processing the sequence forward and backward at the same time, and then concatenating those hidden states.
Which would solve the issue where the meaning of a word depends on context that hasn't even happened yet in the sentence.
Right, it gives you context from both directions. And this is a big, but the theoretical elegance of the RNN completely falls apart in practice when you try to actually optimize it.
Ah, right. The vanishing gradient problem.
Yes, the vanishing gradient. When you train an RNN using backpropagation through time, you're calculating the gradient of the loss with respect to the weights by unrolling the entire network across the sequence.
So by the chain rule, you just end up multiplying the weight matrices and the derivatives of the tan function repeatedly for every single time step.
Exactly. And since those derivatives are smaller than 1, multiplying them together 100 times shrinks the gradient exponentially. By the time the error signal propagates back to the beginning of a long paragraph, it's virtually zero.
Wait, really? So the weights tied to the early words in the sentence just never update at all?
They barely update, yeah. The network effectively suffers from short-term memory loss. It just forgets the beginning of the sequence.
So how did they fix that? Because I know RNNs were used for a long time.
Well, to combat this, the field introduced the long short-term memory network, the LSTM. Instead of a simple hidden state just overwriting itself, an LSTM uses a much more complex memory cell with these learned gating mechanisms.
Oh, like the forget gate and the input gate.
Right, the forget gate applies a sigmoid function to decide exactly which values in the cell state should be zeroed out, while the input gate decides what new information from the current token should actually be added.
So it's actively choosing what to remember and what to forget.
Exactly, and this creates a sort of gradient superhighway. The cell state can carry information across hundreds of time steps linearly, totally bypassing that destructive repeated multiplication.
That's brilliant. And then the GRU, the gated recurrent unit, came later and just streamlined this, right? Like it merged the cell and hidden states so there are fewer parameters, but it still maintains that long-range memory.
You've got it. So now we've got networks that can read sequentially and actually retain context over time.
Hmm.
The next architectural leap is figuring out how to use that context to generate language, moving from sequence modeling to neural language models.
Right, predicting the future. Because statistical n-gram models used to dominate this space, relying on Markov assumptions to predict the next word just by counting frequencies in a massive corpus.
Yeah, but they were severely crippled by data sparsity. Like if an n-gram model encountered a trigram it had literally never seen in training, it assigned it a probability of 0.
Because it treated words as discrete independent symbols, it couldn't grasp that the cat rested on the rug is semantically basically identical to the kitten sat on the mat.
Exactly. And that's where neural language models come in. They solve the sparsity problem by leveraging continuous vector spaces. The embeddings map semantically similar words close together in that space.
So the architecture fundamentally acts as a massive multi-class classifier, but the classes are every single word in your entire vocabulary.
Yes. The generation process is autoregressive. You feed the context into your sequence model, whether that's an LSTM or even stacked causal CNNs, actually, with residual connections to avoid data leakage from the future.
Right. And then the network outputs a dense vector, which is projected onto a vocabulary matrix. You pass those raw logits through a softmax layer to get a valid probability distribution over the entire dictionary.
And then you just sample the highest probability token, append it to your input sequence, and run the entire forward pass all over again to get the next word, left to right.
And training, this is just minimizing the cross-entropy loss between the model's prediction and the actual next token in the training data, right?
Exactly. And when you evaluate these models intrinsically, you use perplexity.
Okay, here's where it gets really interesting for the exam. So perplexity is basically a mathematical measurement of how shocked or surprised the AI is by the real text. So a lower perplexity means the model is smarter because it saw that next word coming.
That's a great way to put it, yeah. It's essentially the exponentiated cross-entropy loss. A lower perplexity means the model assigns a higher probability to the true sequence of unseen data. It's a direct measure of how well it's internalized the distribution of the language.
That makes total sense. But generating the next word in the same language is one thing. Mapping a sequence in English to a totally different sequence in French introduces a huge structural puzzle. Machine translation is a sequence-to-sequence problem, right? The input and output are totally different lengths.
Right, they have different grammatical structures, and there's no strict one-to-one alignment. The initial neural approach to this was the encoder-decoder RNN architecture.
How did that work?
Well, you have two separate networks. The encoder reads the English source sentence token by token. Once it reaches the end of sentence token, it takes its final hidden state, which is just a single fixed-length dense vector, and passes it to the decoder.
And then the decoder uses that vector to start generating French. But wait, the flaw there is pretty glaring, isn't it? You're forcing the encoder to compress the nuances, the adjectives, all the syntactic relationships of an entire 50-word paragraph into one single vector of like maybe 512 dimensions.
Yes. It is an impossible informational bottleneck.
It's basically like trying to memorize an entire textbook, closing it, and then trying to write a dissertation based on the single blurry summary left in your working memory. The decoder is starving for granular context as it writes, but all it has is that initial compressed state.
I love that analogy. And the solution to that bottleneck was the attention mechanism, which was introduced around 2014. The fundamental shift was realizing we didn't actually need to throw away all the intermediate hidden states of the encoder.
Right, so you just keep the textbook open on the desk.
Exactly. By preserving every hidden state from the source sequence, the decoder can dynamically focus on different parts of the input at every single generation step. When the decoder is about to predict a French word, it takes its current hidden state and computes an attention score against every single encoder state.
And the math of that scoring can vary, right? Like, you can use a simple dot product between the vectors or parameterized functions like Badano attention, which feeds the states through a multi-layer perceptron, or even Luong bilinear attention.
Right. But regardless of the function, you end up with raw alignment scores. You apply a softmax over those scores to create a probability distribution, which gives you your attention weights.
Okay, so the decoder might determine it needs to allocate, say, 85% of its focus to the third English token, 10% to the fourth, and distribute the rest elsewhere.
Exactly. It takes those percentages, multiplies them by the corresponding encoder states, and sums them up. That creates a custom, dynamically weighted context vector specifically tailored for that exact moment in the translation.
Wow. And then the decoder uses this targeted context, along with its own hidden state, to finally predict the next word.
Right. And generating that translation at inference time brings up another critical algorithm you need to know: beam search.
Because if you just pick the absolute highest probability token at every step greedy decoding, you risk committing to a local optimum early on, right? Like it might force the model into a grammatical dead end later.
Exactly. It's the exposure bias problem. The model is forced to condition its next prediction on its own past mistakes, rather than the gold standard tokens it saw during training. Beam search mitigates this by maintaining a fixed number of the most probable partial sequences, the beam width, at each time step.
So it keeps a few hypotheses alive at once.
Yeah, it expands all of them simultaneously, calculating the joint probability of the entire sequence, and only selects the optimal path once it hits the end token. We then evaluate those translations using automatic overlap metrics like BLEU or GHRF.
Though those overlap metrics notoriously struggle to capture true semantic preservation the way human evaluation does, right?
Absolutely, you always have to interpret them carefully. But look at the architecture we've built here. We have an RNN encoder, an RNN decoder, and an attention mechanism bridging them.
Yeah, the model can dynamically look at all the source words simultaneously to find the right context, which kind of raises a vital question. If having the book open, if the attention mechanism is doing all the heavy lifting for alignment and context mapping, why are we still forcing the model to read it word by word with an RNN in the first place?
And that is the exact insight that led to the seminal 2017 paper, Attention is All You Need. The realization that recurrence itself was totally obsolete. You can throw out the RNNs, throw out the CNNs, and rely entirely on self-attention. That is the transformer.
The ultimate paradigm shift. Okay, so in the old sequence-to-sequence model, the French decoder was paying attention to the English encoder. But in self-attention, an English sentence pays attention to itself.
Exactly. Every token in the input sequence interacts directly with every other token in parallel. The mechanism operates on three learned matrices: queries, keys, and values. Every word embedding in the sequence is projected into these three distinct vectors.
So if queries are asking, who has this info, and keys are yelling, I have it, and values are the actual semantic info, it's basically like a massive networking event where everyone is shouting at once.
That's a great way to visualize it. When the token bank needs to disambiguate its own meaning, it takes its query vector and computes a dot product against the key vectors of every other word in the sequence. To keep the gradient stable, you divide that result by the square root of the key dimension that's scaled dot product attention.
Got it. So if bank has a high dot product with the key for river, the softmax outputs a high attention weight. Bank then takes the value vector of river, scales it by that high weight, and absorbs it.
Yes. The embedding for bank is mathematically updated to contain the context of river, and this happens for every word looking at every other word simultaneously.
But wait, by completely removing the RNN, you've removed the inherent structure of time. All the tokens enter the self-attention layer at the exact same moment, so the network has absolutely no way to distinguish whether it's man bit dog or dog bit man.
Right, we're back to the CNN's fatal flaw, losing positional data.
So how does the transformer fix that without going back to recurrence?
They use positional encoding. Before the embeddings even hit the attention layers, the architecture injects a mathematical signal, usually a mix of sine and cosine functions of different frequencies, directly into the embedding vectors.
Oh, so everyone at the networking event is basically wearing a name tag with their table number. The AI knows exactly who is standing where.
Exactly. This permanently stamps each token with its absolute and relative position in the sequence. The model processes everything in parallel, but the geometric relationships between the vectors actually encode the original word order.
That is so clever, and the transformer block layers this heavily, right? Like you don't just run self-attention once, you use multi-head attention.
Yeah. Right. You project the queries, keys, and values into multiple lower-dimensional subspaces and run the attention mechanism in parallel. One attention head might learn to track subject-verb agreement, another tracks emotional sentiment, another tracks pronoun coreference.
And then the outputs of all those heads are concatenated and passed through a standard position-wise feed-forward network. And just to make sure the gradients don't vanish when you stack dozens of these blocks, the architecture relies heavily on residual connections.
Yes, skip connections. Literally bypassing the attention and feed-forward sublayers and adding the original input back into the output, followed by layer normalization to stabilize the activations.
And this ability to look at everything simultaneously is exactly why transformers became the foundation for modern NLP. You can stack transformer encoders to build models for deep bidirectional understanding, or use masked self-attention and transformer decoders to build autoregressive generators.
Right, masked, so the attention heads can't cheat by looking at future tokens. That's the complete trajectory. CNN successfully captured local engrams, but discarded long-range syntax. RNNs captured that sequential syntax, but bottlenecked on computation and gradient flow.
Attention solved the information bottleneck by dynamically weighting hidden states.
And finally, transformers isolated that attention mechanism, discarded the sequential constraint entirely, and enabled the parallel processing of massive context windows.
What a journey. So, to you, the listener, you now understand the causal chain of NLP evolution. This is the foundation of the modern AI landscape, and it's exactly what you need for your final exam.
Absolutely. Though I do want to leave you with one final thought to mull over for your prep, something that goes beyond the textbook.
Oh, let's hear it.
The power of the transformer is its ability to compute the exact relationships between every single token simultaneously. But the computational complexity of self-attention scales quadratically with the sequence length. Comparing 10 tokens requires 100 operations. Comparing 100,000 tokens requires 10 billion operations. So as we push models to ingest entire libraries of books in a single prompt, you have to ask, at what point does the sheer density of a massive context window overwhelm the attention mechanism? Is there a physical limit to how much an AI can pay attention to before all those voices at the networking event just turn back into white noise?
Man, a quadratic scaling problem to keep you up tonight. Think about that as you review those architectural trade-offs. Trust your understanding of the math, and good luck on the final. We'll see you on the other side.